Okay, maybe it's time for the talk. Today we're very happy to have Pam to tell us more about the triple product L functions. Please.
Thank you very much for the invitation and the introduction. It's really nice here. So today I'm going to talk about triple product L functions. This is joint work with Jayce Getz, Chun-Hsien Hsu, and Spencer Leslie. So first talk about some background and motivation of our work. And then I will define the zeta integral we define for the integral representation of L functions. And then I'll state the main result. And then I will talk at the last the Braverman method, which is a method we are trying to prove the Poisson summation conjecture needed for the property for the L functions. So I'll start with motivations. So we call the Poisson summation conjecture. So I will start by reviewing the classical Poisson summation formula for vector spaces. So I denote V R. V R to the n. The V Z is Z to the n. And this space emits an action by GL and R. So we are times GL and R. We are sending V G to G in V. And then there's a space of Schubert function on this vector space. So this is the Euro Schubert space. It's a rapidly decreasing function, so VR. And the space emits a Fourier transform. Which is given by F gamma. It's the integral over R to the n e minus 2 pi I gamma x fx dx, where this F is in the Schubert space. And then so there's a Poisson summation formula. That's the sum of gamma in Z of F gamma is the sum of gamma in Z. The Fourier transform acting on F. Yeah. So how is this helpful to us? So while Langlands and Jayce use identical version of this vector space Poisson summation formula to prove the properties for standard L functions for GLN. So from now on, I will denote F as a number field. And A as a del. And then the work of Langlands and Jayce. So the geometric backdrop of the Langlands and Jayce theory is that there exists a GLN cross GLN equivariance. Embedding from GLN to Fn, which is the embedded matrices. So this generalizes the GM equivariant embedding from GM to GA, which is the geometric backdrop of Tate spaces. So this can be think of as a generalization from GL1 to GLN of Tate spaces. And the constructed zeta integral, which they show is an integral representation of the standard L function Ls pi of GLN. I don't know what GLN, right? So there pi is a capital ultimate representation of GLNA. And this is given by ZS FB. The integral over GLNA. FG dg determinant of g to the power of s plus n minus 1 divided by 2 dg. And here F is in the identic Schur space of the vector space M, which can be decomposed into the local Schur space, which at Archimedean places it's just a Euro Schur space as in the classical case. And tensor with non-Archimedean places, which are the space of compact support smooth functions. Non-Archimedean places. And this B is in the future coefficient of pi. And then they prove the global morphic continuation and functional equation of the standard L function by applying the Poisson summation formula. So in this case, it's a sum of gamma in F and F. F gamma is the sum of gamma in F and F. Fourier transform on F gamma. So that's the application of the that version of that to the L functions. Questions so far?
I meant is this n by n matrices?
Yes. Yeah, so it's like n by n vector spaces.
You haven't used these GLN actions yet.
They use it in proving that using that integral and this. Yeah.
But you haven't used it in the talk.
Yeah. So
Tomogawa did this on a division algebra before, actually.
yeah. So this M with GLN cross GLN action is just a special case of a more general setting. So it's called the spectral varieties, which are G variety with open dense Borel orbit. So the work of Braverman-Kazhdan Lafforgue and we have the Sakellaridis. The work implies that there's a what we call the Poisson summation conjecture. So it says for any G or ID X, there exists a Schur space as XA, which can be composed into the local Schur spaces with distributed tensor product. F3. And here, with respect to the basic function, EV as each. Derived by basis. And there's should also be a Fourier transform. Acting from XA to itself. And then there should also be a Poisson summation.
By spherical, you mean symmetric or something more general? Spherical variety.
G variety with open dense Borel orbit.
Ah, okay.
So this should be X in the smooth locus of X that point equals the sum of again smooth locus and the solution for acting on that. X.
About the previous question, do you assume V split or Carry split?
G?
Yes.
Yeah. So then I'll talk about some known cases so far. So first of all, there's what we call the Braverman-Kazhdan space. So which are varieties of the form G not the commutator subgroup of the maximum parabolic of G. Here G is split and simply connected. So this is originated by Braverman-Kazhdan. And then later refined by Getz. And then by Getz Hsu Leslie. And then there's triples of right places. So really by Getz and later refined by Getz and Getz Leslie.
No, I did not read which is X in which case.
What's what you're dividing by? So
Okay. We didn't talk about this parabolic, the maximum parabolic of and then there's my PhD thesis, so I did 4 pairs of correct spaces. This automatic twist. So this is MSL. So which is I did for 0 locus of a pair of correct spaces with a twist by automorphic forms on GLN. Or say integral coefficient of GLN.
So if you do this Poisson summation is equivalent to analytic continuations of certain, just like the above is equivalent to.
This is a goal.
When some of them set it up so as to try analytically continue certain L functions.
Yeah, this is a goal.
So question is, when you prove these cases, what new cases you're not using?
No, this case doesn't imply L function stuff yet. These are purely Poisson summation formula.
Existing of what space, that's a statement or part of the conjecture?
Oh, so the conjecture is just for any super variety X, there should be the Schwarz space and the Poisson summation.
But the definition of the Schwarz space is not obvious.
Oh, what do you mean? I
did not understand if this existence is part of the conjecture, or you say first there is a Schwarz space and then you have a conjecture.
Does the conjecture predict how to construct this Schwarz space?
No. There's no prediction on what this is like, but there should be exist something like with the property that.
Just a funny question. In the cases with like in the GLN case or the 0 locus, that you have an open dense orbit, and then of course the locus where it's 0 like even in Riemann's proof, you have to remove all at one. So how does that happen?
Yeah, I'm hiding some boundary conditions.
Okay.
Yeah, I didn't want to bring it to the picture. Yeah, yeah, good point. Thanks.
What would be the square of Fourier transform?
What?
If you iterate Fourier transform, what would you get? Classically, you have f of minus x instead of f of x.
Sorry, I don't understand.
Fourier transform is not an involution, so the square would be something interesting. Or trivial, perhaps.
Somehow, if you have a functional equation out of it, then you're going to have to understand it, right? The
Yeah.
contragradient somehow.
Yeah. This Fourier transform should have some equivalent property according to this action. Yeah. I forgot to write here. Yeah.
Now, in the classical case, you often have more than just Fourier transform. You have the whole metaplectic book or things like that. One does not want to have more than just one operation.
Sorry. I'm not sure. Yeah. Okay, so there's also should be a case for super varieties, which is by Getz. And then there's also varieties correspond to the mean representations. Of groups of type. Yeah, which is by Braverman-Kazhdan. And then there's also some local cases. He also working both settings by work of Jiang both Shahid Zuckerski and a few others. So the global known cases I have listed just now actually. So there's not many global cases known, and there's kind of more work on the local Schwarz space as in Fourier transform. So it's still a widely open question that to prove the Poisson summation formula for our variety X.
Because you proved the case you said up top there.
Yeah.
Oh, well. Can you tell us what the statement?
Yeah.
This statement with
So-
your theorem.
Like it can be understood as so I define some integral I, which can be thought of as a co-invariant of the price space VA and service, the co-invariant of the reduced representations of H by some parabolic of H and a Whittaker model of tau X, where this H is XO to them plus 1 and the Whittaker is on this G1 pair. So it's going back some as a tau. And then this co-invariant by some and then psi, and this is G is GL2 plus GL2. And then Q a space of smooth function of some y prime. Where y prime is the subscheme of this correct space. And then I prove for I define a Schwartz space of y prime tau as this image of. So this correct space fixed by this particular thing inside the induced representation. Yeah. This is
QN was
some parabolic image here.
an H, okay, so it's the
Yeah.
G.
It's
GLN?
yeah.
Yeah.
Yeah. So let's
What's the source of your proof?
oh
Some is a miraculous thing, so how do you prove it?
I
What do
use
you
some
mean?
quantum equation of some
So you get some-
improvement.
And you use those, or?
Yeah, so I use the implementation so for plus L, and then I substitute this functions here into this SO4 using the central algorithm from SO2 plus SO2 SO4.
I guess are you using the known cases of some Rankin-Selbergs? or something?
Yeah. I use this to accelerate. That's exactly So what we want to do is when we meet the Goldman-Jacquet case to use the Poisson equation. Conjecture to prove the function equivalent. And the memorphic continuation. Of very general Langlands L-functions. And then by converse theorem, this should imply a large part of Langlands functions.
Can I ask a question about the Schwartz space?
Uh-huh.
How do you know you have what you might call the right one? Like if two different people have two different Schwartz spaces, how do you figure out?
So there's in the work of No and Lafforgue, there's some geometric interpretation of what the basic function should be.
But the basic function, right? But the whole Schwartz space? Like over there, you seem to define it in terms of image. I'm just wondering what kind of checks you can do to know that's the morally correct one.
I think they can have different definition here as long as this matches. But
Oh, so okay, so you don't think the Schwartz space is so intrinsic?
yeah.
Okay.
Okay, so this is the end goal of this whole program of Poisson summation stuff. Okay, so now I can turn to the other integral representation. The trivial functions. So I'll first define what we call the triple product. So first, at R1, R2, R3, be positive integers. And then,
What are you on, GLN? or-
yes, GLN, 3 copies of GLN. And then, I denote the tensor of the 3 pi i's, where each pi i's are considered also representations. GLR. And then we denote the triple product. So we built L as pi tensor 3 as a triple pi L-functions, and this is we also written as pi as pi 1 cross pi 2 cross pi 3. And here the tensor 3 is the map of L group of GLR1 cross GLR2 cross GLR3 in the L group of GLR1 GLR3. This is this GLR1 or GLR3C. And then for this triple L-functions, the case when R1 equals R2 equals R3 equals 3 is the smallest case, where their properties are not unique. And the lower rank cases can be proved by the functorial transfer from GL2 cross GL2 to GL4 by Braverman-Kazhdan, and then GL2 cross GL3 to GL6 by Kim Shahidi. But these are the 2 only known cases for the functorial transfer to use here. So that's our motivation to prove for arbitrary rank. And then why we are doing this is we have the analytical properties. Of the triple functions by converse theorem. You can get the tensor product of Langlands L-functions.
Still talking about the equal case.
No, we don't have this.
Sorry?
No, we only have like 2, 3 case because we can use this functorial transform even.
Yeah, right, okay.
But 3 we don't have. So yeah. Okay, so now I'm going to define some group and schemes that used in the group application. So I'll put in this side so it will keep. So I'll denote R as alpha, and then denote HR to be a subset of GL are three. They have three vectors in the R3. And such that the determinant of each vector is the same. And then I have, HE to be an extension of H. So if you know what this is, it's a Z extension in the sense of code-list, but if you don't know, that's okay. I denote X circs to be GL underlined by R minus 2 underline. Here the R underline means the three copies are 1 and 3, so that I don't really out this each time. So and then here on R minus 2, it's the uniform radical of E minus 2 inside GLR. So which is of the type R minus 2. So it's like of the block form effect R minus 2 and 2. So on the right side. Yeah, so and then I denote the X to be the upper closure of X. And then so we have that X is a singular spherical GLR underline plus GLR minus 2 underline plus HE IT. And this is this open form Xer. And then I denote MI as a subset of R minus 2 matrices. Which one subset of rep 1 matrices. And then I denote a max circ. It's MI minus 0 and M2 is 3 copies of MI. Similarly, I'm circ is 3 copies of MI circ. And then we have an action of GR minus 2 plus G of that. And then I denote V3 as G2 tensor K2 tensor J2, which has an action of H. So there's an action of HE on the H factors. And then we construct a singular closed subscript which we call a Y inside cross. So those two we are using a product of X and Y here. So X is a singular supervised and yeah.
Could you tell us how you come to this definition rather than give us the definition?
So at first we are trying to use the Poisson summation Schwarz space of the Braverman-Kazhdan space to try to prove for things, but in time we realize it's not enough after we try to construct the zeta integral for it. But so we get to here. This is correspond to Braverman-Kazhdan space.
So what features, like you're looking for a specific L function.
Yeah.
So what feature does the space have to match with your desired L function?
So one has it's a sort of security writing using this GLR here.
Mhm.
We try to use unknown things to figure out if we can get something worked. But then later on we figure out this is not enough, so we're enlarging this to GLR minus 2 to make things non-vanishing. Yeah, and then yeah, it's like too complicated. I don't know how to explain it. Yeah.
So you're enlarging GLR,
Yeah.
adding like a copy of GLR minus 2, and then there's this H is like inside the three products of GL2s. Is it?
Yeah, so there's actually like sort of this on the right hand side and then some space here and then this GLR minus 2 is here. Using G prime and then like this HE is in this block. Yeah.
Oh, that's I mean, it's again sort of decomposing a GLR into R minus 2 and then matrices of that form.
Yeah.
Okay.
Okay, so now I can talk about the interrepresentation, which is we built using some equivalent tensors over x cross y, which I defined there. And then talking about the tensor. So consider an R minus 2 group tensor of GLR cross y to x cross y. And then this is GLR cross J minus 2 cross HEV equivalent. And then we define a morphism. Of the track in the side from GLR. And then I plus y then R minus 2 to G8. Then we are gathering this pair of the tensors GLR plus y to plus y. And then this morphism psi. So we use abstract the key property of these pairs to define certain notion of like psi functions. This is underlying our the geometry setup of the underlying our work. And here's a remark. So this notion of alpha Einstein bundle is related to vector reductions. In the sense of the context. So from the vector induction to define, one can get alpha Einstein bundle using this. So this is sort of the relationship. And then using this morphism psi and this an additive non-trivial character. We do this little psi. And then we construct a Hermitian vector bundle with no E psi and over this exert A equals Y. And then so smooth sections here are smooth function on this GL R cross Y, which says some properties according to this psi and this psi on the input radicals. And then for super sections F of E psi over X cross Y, the A points, and also we have G prime H in GLR A cross GR minus 2A cross H in A. We construct zeta functions, which is defined to be the sum of S Y in S cross A Y of this action of R G prime H of this functions S cross Y. So and this it uses whenever this is convergence.
What's our here?
Sorry?
What's our here?
So whenever this is convergent, we use this zeta functions.
The question,
On the right hand side.
Oh, it's the action of this groups on this schemes, but on this F, on this in the space, like realize on the
Sum over these.
Somewhere.
so I'm sorry, yeah, good catch. Yeah, why? Yeah. Yes, please. Thanks. And then I have V and V prime are customs. Of VR and VR. Okay. And then we have zeta integrals ZF V prime. S and then S. Via integral over ultimate quotient of GR plus GR minus 2 plus E.
So if you were doing Garrett's triple product, this would be, you would
Yeah,
do
yeah.
exactly Garrett, right?
Yes.
That would be the theta ordinary simplicity.
Yes. Yeah. Just don't have the actual structures on R minus 2 parts. So this one is bigger. So prime H, V prime, G prime, and some multiple characters on EH or G prime H. AGDD prime H. So this is our global zeta integrals.
The variable S.
Just 4 variables. S1, S2, S2, S3, and S. Yeah. But our trivial function is related to this S. Okay, so now I can say the first issue. For the real part of S of the life as easy R4 greater than 0. In super non-approved. We have Z, have B prime, and S. And after the unfolding, we get to a Eulerian integral. So this is completely certain.
So is that where the use of the open orbit? What's giving you an Eulerian?
We expand this.
I mean, usually you need some uniqueness there.
Yes, on this phi and phi prime.
And that has to do with this action being this homogeneous vector space.
Yeah. And so this can be written as HE for the center of HE and some independent subgroup of HE and then A equal of GR minus 2 over the maximum independent radical of the variable. Yes. Sorry. Similar for GR, the U are and then the vertical function correspond to psi and phi and psi bar and phi prime. And then this is cross R, G, and H acting on at the identity points, and this is a representative of the open orbits of the GL2 minus 2 cross HE action. And then there's again this character. Yes.
I also have a funny question. You work in these pre-homogeneous vector spaces, basically, and there's this Saito-Shintani zeta function, which is somehow constructed using Poisson sum. Is that any relation to anything you're doing? Because that is sort of seems like the most primitive aspect of what you would be doing. You know those functions? They use Poisson sum and then they analytically continue these weird functions.
I'm not sure. Not yet about that. I'm not sure.
I guess the thing that you have arranged is to have an Euler product. Does that. Okay, you're going to tell us what you know about the function of S here, right?
Yeah.
What's the eta in the integral?
Multiple character. So it's like some that G to the S.
Okay. There's nothing else that depends on H, just theta? Sorry, in the top integral, the top board.
Here?
No, on the board on top, there's an H inside of theta.
Yeah.
Is there an H anywhere else?
There's this character here, but there's not.
Oh, sorry, there's an H there, I just couldn't see it. Thank you.
Sorry about it's like it's a corner.
what did you write below that integral? Like, same integral, the one above, and then black square above. So you're integrating over GLR, etc., and then you say diagonal. No.
No, DG, D prime, DH. The variables of integration.
I see. So how do you recover Garrett's formula? As you was asked before, you said that GLR minus 2 disappears, right?
Oh no, that's R1 equals R2 equals R3 equals 2. Okay.
Yeah.
But we are dealing with greater than 3, like greater or equal to 3.
So you're okay.
Yeah, we are doing the general larger. Right. Okay, so now, so since this is Eulerian, so we can like factor into the local integrals and compute it. So maybe I'll jump to the yeah. So we have a very explicit computation formula with to come. Like it's time consuming, so I'm not writing this up here. But the corollary of the explicit formula for that is, so assume pi prime and psi identified. And then this W naught and W naught prime is in the vector identified vector model. Such that it's normalized to be the Euler identical quantities. 1. And then that's epsilon greater than 0, and for real part of S and the real part of size greater than epsilon. We have this Z, the student for Z W. A naive basic functions as underlined as pushed out by this LS1 half into tensor 3 is the triple parallel functions we want that with pi 2 plus rendering that. And then we have 3 copies of the ranking suburb.
This is in the denominator?
Yeah. Yeah, I'm going to say this is 1 plus something. So this is just some combination of SI and S plus 1 half. So this is a local ranking suburb functions. And then we have the local center of functions, pi 2. So we have shown that this quotient is 1 plus the big O term of epsilon Q minus 1 minus epsilon. So this is approximately the triple of functions we want. And the ranking suburb of function we know their properties of. And then the standard of function also know their properties of. So this is approximately the interrepresentation one. And here we only put, so this be naive is the approximation of the actual basic functions. And we expect that there's a true the basic functions here to subsphere so that the above quotient is 1.
So what is the right hand side? What read equals?
Equals 1 plus the big O term of Q minus 1 minus epsilon.
What is Q?
It's the
Resurrect.
yeah.
What?
The unit binder, the norm of unit binder universe.
This is a local state.
Yeah. No.
Yeah. So the bulk of this one. Okay, so we now have other than this issue of the Braverman function, we have a representation for the triple L functions. Now we want to use this to prove the properties of the L functions. So then we are lacking of some sort of Poisson summation formulas. And then our next theorem so use the zeta integrals and assume that we have the Poisson summation conjecture for this alpha side boundaries. So the geometric object underlying our work. So, and together with some local compatibility properties like that, the extent of this true basic functions and also some equivalent properties properties. And we have, so this is one conjecture, this is another conjecture. And then this is the triple L functions we want and these monomorphic continuation to the plane.
So
Yeah.
whatever you're doing, you're only approximating the Euler product and the region of convergence up to some accuracy. So often these functions have natural boundaries. How do you get around that? You know what I'm talking about? You might have an Euler product that to leading order looks like a standard L function, but then it's got some lower order p to the minus 2s, which creates new poles to the left. Where are you dealing? I mean, you seem only to be writing. I don't like this 1 plus over.
Yeah, we assume we can get rid of that 1 plus the plus thing. Yeah, that's this assumptions here. Yeah. Yeah, we have made some assumption locally, so things are getting fine. We are using the function equation of the zeta integrals. And then so there's 2 things left for the whole game. So one is this Poisson summation formulas. Another thing is how to deal with this local compatibility. So now also we are currently dealing with the first one. And we have that's the next thing I want to talk about is the fiber bundle method.
So at this point, you're dealing with 3 guys on GLM quite.
Yeah.
Would you even be able to tell me when that has a pole?
Not yet.
I mean, where would it come from from the ashes? Where would that come out? That's one of the hardest questions is to know when Rankin-Selberg L functions have poles. At 1. I'm talking about a pole at 1.
I'm not sure yet. Yeah. Okay. Yeah. Right now we're just dealing with Poisson summation. And now, so the strategy we use is suppose we are given a diagram. These things. X to some B1 to some B2. We call the first map P1 second map P2. And the fiber bundle method is so if we have the Poisson summation conjecture for the fibers, Pi inverse of Bi for some Bi CG, you can this will imply the Poisson summation conjecture for the X we want. So this B1 and B2 has to be So for our case at hand, we have this x cross y. We have two maps from x cross m, and then other two is 3. And we call it this is P1, this is P2. So we have the fibers of U1 are vector spaces. So which is fine. We know the product summation formula for the vector spaces. Point is how to do the fibers of V2. So these are simpler Poisson bundles. And so this is the 0% summation formula are approachable using some spectral method. So using control. Basically, we spectrally define expand the functions, and then we define the Fourier transform using the control formula. So this is going work. Going work in this calculation. Yes, that's true. So we are almost done, except checking some property of the Fourier transform. So we hope to get this finished soon. So we have this fiber, and also we're proving this. And then the next step is to combine them to get the Poisson summation formula for this. Then we can finish the first part of this. And then what we left to do is the second part. So in Go's several works and talks, he said so the key is to bring down the global superiority stuff to the local things. So we are doing the exactly same thing. That we are breaking down the global things to local things. So hopefully we can use some of the local work of the Schur spaces to tackle this, but we are not yet sure about it. But we have hope. So I think that's all of my talk. Thank you.
Are there any questions to the speaker?
What do you know about Z before the Poisson sum is applied, and what do you know about Z?
So we proved the functional equation of C and
With these multi-S's?
Yes. Again, assuming some local things.
And how do you deal with the, or the cusp form somehow? What about the zero set of this pre-homogeneous vector space? It doesn't play a role. It's not a point. It's not easy. At some point you're applying Poisson sum. It says you sum over all the points equals the sum of the. Where's it captured?
We haven't combined this part. So we haven't combined those two into that, so we're not sure yet.
So that's why I'm asking, what do you know about Z itself? You know that Z is meromorphic. How do you prove that?
By assuming that is one, and also based on some assumptions which haven't been proven. Yeah.
When you say meromorphic, you know about the pools or
not? We proved the property for Z, again assuming this.
Yeah, may I ask about, you mentioned about the spectral methods, right? By the punctual formula, the punctual formula for which space or which group that allows you to prove the Poisson summation formula?
Like the fibers here is like some X cross FL, some L in Q. And we are using the Harshchandra space for T. Like we are having this Harshchandra space that we are putting down to something like C X cross that. And then we are using the temporal formula here to eliminate theorem to temper and we are using Fourier transform here to get down to H.
So how about for the unramified calculation over there? So it should be some sort of like combinatorics problem in some Schur's polynomial. Is it a priori clear that you got the triple product L functions, and how do you get the rest of the L factors? Is there some sort of like telltale sign to see they are the right L factors to compare with? Or is it just a bunch of?
I want to factor out this triple first. And then,
how about the rest?
Yeah, then
You're asking a really hard question. Even in Rankin-Selberg theory, the Archimedean place, I don't think it's ever been done.
yeah, like the Rankin-Selberg comes up from just GLR across GLR minus 2 part, the phi. And then, and for the rest, it's just, we put in this old terms or whatever in the rest.
However, if you do that all unramified places and it's up to a rational function, then I give you that you meromorphically continued it.
Are there more questions to the speaker? If not, let's thank the speaker.